Good afternoon, students. Today we are going to study very important concept, that is your crystal field theory. Before that, we should know we have studied already the valence bond theory proposed by Pauling, where we consider the interaction between the metal and ligand is covalent, right? So where there are certain limitations in valence bond theory, VBT theory, that is mainly it could not explain the spectral properties of your complexes. Also, it could not account for the magnetic property for certain complexes, right? So in order to overcome the limitations of VBT, we have come across a new theory, that is what your crystal field theory. As the name says, there is a name called field theory. We deal with your electrostatic field. Okay, now before that we should know that the interaction, you know that coordination complexes are mainly found by your transition metals like 3D, 4D, 5D series, right? So well known example is your all your 3D series like scandium, titanium, zinc, zinc, iron, cobalt, etc., right? So very important concept that you should know is interaction between your metal and your ligand, right? Metal ligand, whereas in VBT we consider this to be what, covalent, whereas in your interaction in crystal field theory it is nothing but your electrostatic interaction, electrostatic. Why we should study this theory will give you the electronic structure of the transition metal complexes. Mainly transition elements means d block elements, right? And very important thing is it consider the energies of a d orbital of metal atom are affected by your electric field. See, we know that when you observe the electric field where there is a there's a charge separation, or also when two charged particles come together, right? So here we consider your metal as your positive center and ligands to be a negative center. So when they interact, the interaction is said to be purely electrostatic. We are not dealing with your covalency, or covalent character is not dealt in your crystal field theory, right? Next, the interaction between, very important, the postulates, the interaction between the metal ligand is purely electrostatic in nature. And very important thing is we are telling interaction is nothing but, we know that metal is, this is what we represent a coordinate bond where ligand donates a pair of electrons. Like ligands are of two types that we have studied. They are what, they are generally called as your Lewis bases. Lewis bases, what, they donate a pair of electrons. The species which donates a pair of electrons are referred as Lewis bases. Next, species with accept are called as Lewis acid. This is electronic theory proposed by Lewis, G.N. Lewis. So ligands donates electrons to the metal d orbitals, that we should know. Okay, now we consider ligands to be we have classified ligands as monodentate, bidentate, tridentate, hexadentate, polydentate, etc. Generally they are anions and your neutral ligands. We cannot take cations because they are electron deficient. As I have already told, it's a Lewis base which donates. So anions like chlorido, cyanato, and you can take other anions like so there are so many ions, generally halogens, cyanide, etc. And you can take neutral ligands. Neutral means the charge should be zero. Example, water, aqua, and amine complexes. We can take ammonia, we can take CO is what, carbonyl, right? So they are all neutral ligands. So whenever the anionic ligands, we saw they are electron rich, right? Whereas your neutral ligand, how they interact, see, we know that if I consider this to water molecules, we know that water molecules is having what, dipole moment, net dipole moment, right? So we have net dipole moment. So we have a dipole moment, we have negative dipole, positive dipole. Your metal is your is in positively charged. Whenever positive charge, the negative part of your dipole interacts with your what, your metal atom, that you should know. So in neutral ligand, negative part of a dipole interacts with your metal atom. So this is very important. Now I will be dealing with your very important thing is your crystal field, where what happens when the ligand approaches the metal atom, how the metal atom, mainly when metal atom means what, metal atom consists of orbitals, mainly the d orbitals. What happens to the d orbitals we are going to see now. Yes, now Before that, we know the transition elements or d block elements. Why we are calling d block elements? We know that when you add an electron, it goes to the d orbital, right? So if we consider 3D series, it will go to 3D shell. Okay, we know that d orbitals is what? D orbitals is 5 degenerate. What do you mean by degenerate? Degenerate means orbitals having same energy. So only we have d orbitals, we have 5 orbitals having similar energy. And what is the shape of each orbital? We know that dumbbell because of 2 nodes. This concept, how we determine the nodes, we'll study in the next coming video in your atomic structure and quantum mechanics. Okay, so there are 5 orbitals. We'll see the shape of the orbital. First is dxy, dyz, dxz or zx, and dx square minus y square and d z square. First is dxy. What? Dxy is orbital which is in between the x and y. This is the axis. This is in between the x and y. Dyz is in between the y and z. Dxz is in between the x's and z. So I'm showing here this is in between the x and z. We know that all the three will be perpendicular. We know that x, y, z. You should remember. So very important thing. Next is your dx square minus y square and dz square. This is your square. It is along the axis. See, along the x-axis this orbital is placed, and your y along this y axis your this orbital is placed, and z square is also along the axis. So very important thing, your dxy, dyz, dzx is facing in between the, not directly facing the axis, it is in between, this in between the axis, in between the axis, whereas dx square minus y square are directly facing the axis, directly facing the axis. Okay, next thing is your splitting, octahedral splitting. Octahedral splitting. As I say octahedral, the first thing you should have that it is what? It is having 6 ligands. 6 ligands. 6 ligands. Okay, 6 ligands. Metal is surrounded by 6 ligands. So you can take so many examples like cobalt amine complexes, cationic complex, or you can take any complex like anionic complexes, etc. You can do any of, you can take any where coordination number is equal to 6, right? This is your coordination number. This is your secondary valency. We have studied Werner's theory. So what happens in your octahedral splitting? Whenever your ligands approaches your metal atom, say it is an energy axis I'm taking, this is your d orbitals. How many d orbitals are there? dxy, dyz, dzx, dx square minus y square and dz square. So what happens when this is a metal atom, free metal atom, say free metal atom or ion, whatever. So what happens when ligand approaches? When ligand approaches, what happens? We know that your orbitals, when ligands approaches, these orbitals also, this metal also possess d electrons, right? These d electrons will, this is negative cloud of the d orbitals will repel your incoming ligands. Say example, your chlorido ligand is approaching. What happens? These two undergo repulsion. What happens when the repulsion is more? They are what? The energies, there will be redistribution of energy takes place. Very important, redistribution of energy takes place. What happens is your degeneracy will be broken. When the ligand approaches, it will be slightly what? Raised in energy. This will be slightly raised in energy. This d orbital is slightly raised in your energy. So we can call this is in the presence of hypothetical octahedral field. Okay, when the ligand approaches, the degeneracy is broken. Degeneracy is what? Having same energy. Now what happens? They split into two, where there will be a difference in energy. See, one thing you should remember, whenever, see, this is your octahedral. If I take, this is your octahedral complex, we know that this is metal atom is here, and ligands, this is your octahedral, right? Octahedral 90 degree. See, we have already studied the orbital concept. Whenever these orbitals of metal atom, it is in between the axis. What are x, y, y, z, zx are in between, whereas x square minus y square and z square are along the axis. So what happens? See, if these ligands are approaching in this x, if I consider this is the axis, it is directly facing. So your ligands like x square minus y square are facing directly the ligand, whereas xy, yz, zx are in between the axis. So whenever the interaction is directly, like example, it is directly facing, that will be more destabilized. More destabilized means what? Stability will be less, so it will be having higher energy. So what happens among this, it splits into two. One is your, it splits into two orbitals that we set is called as Eg. See, remember, E represents to 2 whenever dimensions will be 2. Whenever next is your triplet, that is what? T2g, Eg and T2g. So what are the orbitals which will be lowered in? See, this is energy axis. Lower energy means greater stability, right? So dxy, dyz, dzx, and this, what is this? Dx square minus y square and dz square. This is what your splitting takes place. And we know that the energy between this, the energy between these, splitting energy is nothing but CFSC. This is crystal field splitting energy, represented by delta, or also called represented by delta and dq. Okay, and since we are dealing with octahedral, delta O, delta O represent delta O, or also it's given by 10 dq. What is dq? Is this called as differential quanta. This is to calculate, we have different formula for dq also. Okay, d and q. So we keep the splitting energy in terms of dq values. Okay, like we keep your magnetic property, the magnetic magnetic moment mu is in Bohr magnetrons, like that we keep in CSFE in terms of dq units. Okay, now what happens, this energy is equal to 10 dq. So this is called as barycenter. This is called as barycenter. So whenever the splitting takes place, this is lower in energy, right? How much it is lowered? So there are 5 orbitals, right? It is lowered with respect to what? It is lowered with respect to 2. With respect to 2, it is raised, it is raised in energy, it is raised in energy with respect to what? 5. There are 5. It is raised in energy with respect to 3. So lowered in energy minus, this will be plus. I can write this as how much? 0.4 minus 0.4. This can be plus 0.6. This is what your splitting energy, very important, you should remember. So T2g and Eg set. So now you can calculate the splitting energy, that is delta O. You can calculate, see, based on the amount of electrons, that is what you can if I consider this is T2g, if I consider the x be the amount number of electrons, it depends on the complexes. Okay, into minus 0.4 plus y into plus 0.6. This is your give the crystal field energy. Okay, we can calculate using the by knowing the amount of unpaired electrons, right? It depends on the complexes where it forms high spin or low spin, like that we have to determine. Remember, this splitting always occurs in the complexes, right? This is what you have to know in the what is this octahedral splitting. Just remember how the energy is raised. It is split into 2 levels, Eg and T2g. The total energy is delta O, and is equal to 10 dq, and this is 0.4. See children, you can keep in delta O units, or 10 dq means into 10, that is 6, and this is 4 dq, plus minus 4 and plus 6 dq. Okay, that you can keep, you can remember in any terms, 2.5 delta O or 3.5 plus. You should always remember it is raised in energy and lowered in energy. This is what you are splitting in octahedral field. Next important thing is splitting in tetrahedral. Tetra means what? Tetra means tetrahedral. Tetrahedral means what? The coordination number is 4. Coordination number is 4. See, we have to deal if coordination number 4, you can have 2 types, right? Coordination number 4 means you can have 2. One is tetrahedral, another one is square planar. Square planars. I'll give one example, like NiCO4. This is your tetrahedral complex, whereas similar NiCN4 example, this is square planar complex. See, they are having same coordination number, but splitting will be different because square planar splitting is different from tetrahedral. Now I will be dealing with your tetrahedral splitting. Tetrahedral splitting takes place. Similarly, we know that metal will be having how many? This one. First I will tell you what is tetrahedral. See, if I take a cube, if I place a metal atom here, one ligand will be here, one ligand will be here, one ligand will be here, one ligand, alternative corners will be there, students, like this one. When I join this, this is a exact tetrahedron, this is a exact tetrahedron. What happens? Angle will be what? 109 degree 28 minutes. Okay, now what happens when I take a tetrahedral complexes? If I, this is a metal atom, ligand, 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 right? See, whenever the axis, if I take like this, x y z, x y z, now what happens? They are not facing directly, right? Ligands are not approaching along the axis, right? Because of the tetrahedral angle, ligands are not approaching along the axis. So what happens? Whereas in octahedral, your ligands are approaching along x y z axis, right? So what happens? Your dx square minus y square and dz square, which are directly facing, are raised in energy, so only less stability. Whereas here it is approaching in between the axis, ligands are approaching in between the axis. This is x y z, this ligands are approaching in between the axis. So what happens? It takes reverse, right? Whereas dx square dxy yz zx are raised in energy, whereas dx square minus y square and dz square lowered in energy, just it is changing. So I will show you here. This is your d orbital free atom. We should know dxy, dyz, dxz, dx square minus y square, dz square. Okay, it is raised in energy. Hypothetical which field? Tetrahedral. Tetrahedral field. How many ligands? 4 ligands. Okay, similarly they will be raised in energy and splitting takes place. Splitting occurs. What happens? It is splitted into T2G and EG. What is dxy, dyz, dxz, dx square minus y square, dz square. See students, we should not, this is E and T, T2. We will not write G here, because you should remember this. Why we will not write G means, if I take octahedral complexes, this is your octahedral complex, right? There is I. When I keep this point and inversion, when I do inversion, we get same configuration. If I invert the molecule, you will get the same molecule. Whereas your tetrahedral, if I invert, see this is your tetrahedral, means if I invert, it will not give back your original structure. So we don't have I. I is nothing but inversion operation. We call it inversion. So generally we won't write G here. This G stands for, students, G stands for gerade and U stands for ungerade. Okay, we won't write G here. We generally say E and T2. Okay, just remember octahedral is reverse of your tetrahedral, whereas T2 is raised in energy. Then now what is the energy here? This is your barycenter, means what is the energy here? Delta. If we are dealing with tetrahedral, so delta T. Delta T tetrahedral. Similarly, what is this what will happen? This is 5 orbitals are there, 5 orbitals are there. Reverse it. What was there? This will be 3, it is raising minus, this will be 2. That's all. Just you should revise. It is decreasing with respect to T, it is increasing with plus increasing. So just you should know, and this will be equal to again 10 dq. Okay, and very important thing you should know is, this is raised in energy. Relationship between delta O and delta T. See how many ligands are there? Octahedral, how many you should always remember, should write the energy axis. Octahedral and tetrahedral. How many ligands? 6. How many ligands? 4. See, greater the ligands, greater is the interaction, greater will be the splitting energy. Greater the ligands, greater is the interaction will be more, and greater will be the CFSE. So we should remember delta O is always greater than delta T. Delta O is always greater than delta T, and the well-known relationship is delta naught is equal to 9 by 4 times the delta T. You should remember, you see students, you can also determine this value in terms of delta O only. If you know delta O, you can easily calculate delta T. If you know, if I say example, delta O is around 0.5. If we calculate delta T is what? We have the relationship what? We know the delta O, just cross multiply. Delta O is 0.5 into 4 divided by 9 is your delta T. You should know this relationship is very important. So now we have covered your splitting in octahedral splitting and tetrahedral splitting, where octahedral where how many ligands are there? 6 ligands, whereas tetrahedral we have 4 coordination. Whenever you say coordination number 4, we have tetrahedral and square planar. The splitting should be like this, and you should remember how the splitting takes place and to represent two sets, and we should know that we should always write the energy associated with this orbitals. So in this video I think you are understood what we are going to study here, and I think you have understood how the splitting takes place in your octahedron tetrahedral field respectively. Thank you students. If you have any doubt, please comment and I will clarify your doubts. Thank you.